gamma A00 can be written as half GAK minus del K G00 plus del 0 GK0 plus del 0 G0K. Since the field is static, we can definitely make these two terms to be equal to 0. Static means there is no time dependence in the metric, and therefore the time derivative of the metric should give us 0, because field is static, it is not changing with time, therefore del 0 GAB is always 0. Therefore our job is even more simpler now. Gamma A00 is half with a minus sign, minus half GAK del K G00. And then we have to apply the field is weak. This condition has to be applied. It allows us to decompose the metric into Minkowski form plus a small perturbation. So weak field limit means, weak field limit or weak gravitational field limit means that I can write my GAB as a perturbation over the flat Minkowski space, which is written by eta AB plus HAB, with the condition that HAB is less than 1, so that H or its derivatives can be neglected up to second order, after second order. Also note, we have to note that as GAB reduces to eta AB when there is no gravity, HAB can be thought of as a small perturbation over eta AB. Okay, this is an important point, because what we have said is that GAB should reduce to eta AB when there is no gravity at all. Now suppose you are putting some small very weak gravitational fields into picture, and then what will happen is that HAB can be thought of as a small perturbation over eta AB always. So if we now want to write GAB upper, you have to say that this is eta AB, but then there will be a minus sign which will come into play, and it will become eta AB minus HAB. Okay, in fact, since we are working with Minkowski metric now, we will say that the raising and lowering are being done with respect to the Minkowski metric itself. That means HAB can be written as eta AC, eta BD times HCD, and to first order in H, this can be, so let us also write this to first order in H, that is, there is no higher order terms. We can use G mu, or let me write it in terms of notation, GAB, GBC as delta AC. Can use this. The whole idea is, in the absence of gravity, space-time is basically flat, and in the weak gravity limit, space-time is almost nearly flat. This is defined as a manifold on which coordinates exist, in which the metric has components which is written by eta AB plus HAB, with this HAB being much less than 1 everywhere in space-time. This is true everywhere in space-time. That is extremely important point to mention. Now it is important to say that there exist such coordinates. There exist such coordinates rather than saying for all coordinates, since one can find coordinates where in Minkowski space-time in which even in Minkowski space-time in which GAB is not chosen to the simple diagonal form, which is minus plus 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 1 of eta AB. On the other hand, if one coordinate system exists in which equation 2 is true, I mean that means this basically this is what I am talking about. This was equation, no, this was equation 4, I think. So this, when this equation 4 is true, then there are many such coordinates. Okay, so the idea is that if one coordinate system exists in which equation 4, that means this equation is true, then we can say that there exist many such coordinates. Okay, so now let us look at this expression again, gamma a 0 0, which is equal to minus half GAK del K G00. So let us multiply by GAB gamma A 0 0, which is equal to minus half. When I multiply by G lower AB, then G lower AB with G upper AK gives us 1 delta KB and then del K G00. This is therefore minus half del B G00. Now we are going to use this condition GAB is eta AB plus HAB. Since eta AB is constant, then this must have only del B of H00, right? Because so now instead of GAB we will use eta AB plus HAB, this into this equation. Okay, this we will use now, because this is what our weak gravitational field means. It's a small perturbation over the background metric, which is eta AB. So GAB gamma A 0 0 is therefore can be written as eta AB gamma B 0 0. Why can I write that? This is also very interesting. So this is up to first order, or up to leading order rather. It is better to write up to leading order. This is simply because when I write down GAB as eta AB plus HAB, then I also have to remember that this gamma will have the product of derivative of the metric with the metric itself. So this gamma will have G multiplied with del G, this type of terms. There will be 3 such terms, and everywhere I will expand this G by eta AB plus HAB. Here also this G will be replaced by eta AB plus HAB, but then eta AB, derivative of eta AB will always give us 0 because eta AB is a constant. So this derivative will always act upon H. So we will have terms like either eta times derivative of H or H times derivative of H, both of which are second order in H. Therefore we can all neglect these terms. Only the non-vanishing term that will remain is basically the eta AB times the gamma B 0 0 term. Okay, so eta AB gamma B 0 0, this will therefore be minus half del B H 0 0, because del B of eta 0 0 is always 0, so it will be just del B of H 0 0. Now we can write this, since eta AB is diagonal, we can write this as minus gamma 0 0 0. This is equal to minus half del 0 h00, and of course this is 0 because there is no time variation in GAB, therefore it is expected that there will be no time variation in HAB also, because space time is static. And if we look at gamma alpha 00, I hope you understood why the minus sign is there, because eta 00 is -1. That is why there is a minus sign. So gamma alpha, that means the spatial, alpha means the spatial part. Gamma alpha 00 is nothing but minus half del alpha h00. Therefore, the geodesic equation should look like d2xa d tau 2 gamma a00 dt d tau whole square equal to 0. This was the form of the equation. This will therefore look like d2t d tau 2 equal to 0. This is because the time component involves gamma 000 in the second term above, and gamma 00 is already we have seen is equal to 0. This is one equation that you will get. And secondly, d2x alpha d tau 2 plus gamma alpha 00 dt d tau whole square equal to 0 will be this will imply d2x alpha d tau 2 is equal to half del alpha h00 dt d tau whole square, because we have already seen gamma alpha 00 is equal to minus half del alpha h00. This is what we have already seen. So this is the, and then this implies d2x alpha d tau 2 is equal to half del alpha h00. In fact, I think I have written it wrongly. This should not be tau, this should be t. This should be t. d2x alpha dt2 equal to half del alpha h00. Yeah, so what I have done here is that I have simply divided by dt d tau whole square both side. So this is dividing by dt d tau whole square both sides. So this becomes 1, and d2x alpha d tau 2 divided by dt d tau whole square will give us d2x alpha dt2. This begins to look like a Newtonian theory of gravitation, right? Because this is like a acceleration term d2x alpha, and these x alphas are only the spatial components of the position 4 vector. In fact, you can compare this equation with minus gradient of phi, and see that these are the same. We can see that this equation and this equation are basically same if we identify minus 2 phi as h00, or in other words, G00 equal to eta 00 plus H00 is equal to minus 1 plus 2 phi. Therefore, we have shown that the curvature of space-time is induced sufficient to describe gravity, is indeed basically so induced by the even by the weak gravity approximation, and it is sufficient to describe gravity in the Newtonian limit as long as the metric takes this particular form. Let us call this equation 5. And it remains, of course, to find field equations for the metric that implies that this form, which is given by equation 5, and that for a single gravitating object we recover basically the Newtonian formula, which is minus gm by r. It has to be proved sooner or later. So what still remains is basically finding the field equations for the metric, and that we will do